Labels and ground truth form the foundation of most machine learning systems. They define what the model is supposed to learn and how success is measured. Without labels, supervised learning cannot function, and without ground truth, model performance cannot be meaningfully evaluated or trusted. Labels matter because they guide learning. They provide the reference outcomes that models attempt to predict. If labels are incorrect, inconsistent, or poorly defined, even sophisticated algorithms will learn flawed patterns and produce unreliable results. A label is the target value associated with an input example. It represents the correct answer according to some standard. In classification tasks, labels are categories. In regression tasks, labels are numeric values. Machine learning relies on pairs of inputs and outputs. Inputs describe the situation, while outputs define the desired response. Learning consists of mapping one to the other. Supervised learning uses labeled data to guide training. The model compares its predictions to labels and adjusts parameters to reduce error. Labeled data consists of examples where the correct outcome is explicitly provided. This allows precise error measurement and structured learning. Unlabeled data lacks explicit targets. While useful in other learning paradigms, it cannot directly support supervised training. Semi-supervised learning combines labeled and unlabeled data. It seeks to reduce labeling costs while still benefiting from guidance. Ground truth refers to the reference standard used to define correctness. It is treated as authoritative during training and evaluation. Ground truth is often established by human judgment. Experts define what counts as correct based on domain knowledge. Labels are not always objective. Different annotators may interpret the same example differently, introducing variability. Ambiguous cases challenge labeling. Some inputs do not have a single clear answer, forcing simplifications. Annotation is the process of assigning labels. It may involve experts, crowd workers, or specialized teams. Guidelines help reduce inconsistency. Clear rules ensure annotators apply labels in similar ways. Label noise occurs when labels are incorrect or inconsistent. Noise limits achievable performance. Noisy labels mislead learning. Models may fit errors rather than meaningful patterns. Bias in labels reflects human perspectives. Social and cultural assumptions can become embedded in data sets. Systematic bias scales with deployment. Once trained, biased models propagate those patterns widely. Class imbalance occurs when some labels are much more common than others. This skews learning. Rare events are hard to label. Lack of examples reduces detection accuracy. Labeling is expensive. It requires time, expertise, and coordination. Scaling annotation introduces logistical challenges. Quality control becomes harder. Automated labeling trades accuracy for speed. Weak supervision can help, but introduces uncertainty. All labeling involves trade-offs. There is no perfect solution. Active learning reduces costs by focusing labeling on uncertain cases. Human-in-the-loop systems combine automation and oversight to maintain quality. Quality control detects errors early. Reviews improve reliability. Inter-annotator agreement measures consistency. Low agreement signals ambiguity. Ground truth is context-dependent. Definitions vary across tasks. Labels may change over time. Updating ground truth is necessary. Domain knowledge shapes labeling. Generic labels rarely suffice. Medical labels illustrate uncertainty. Diagnoses often involve probabilities. Language data reflects interpretation. Meaning varies with context. Social data embeds values. Labels may reflect norms rather than facts. Ethical issues arise when labels cause harm. Careful design is required. Transparency helps users understand limitations. Documentation matters. Datasets should record how labels were created and by whom. Training outcomes depend on labels. They shape learned behavior. Evaluation metrics also depend on labels. Errors in ground truth mislead assessment. Feedback loops can reinforce label assumptions over time. Deployment magnifies labeling mistakes. Errors affect real users. Continuous review improves reliability. Labels should evolve. When labels fail, systems fail. Limits must be acknowledged. Not all problems can be labeled effectively. Alternatives exist. Signals beyond labels include feedback and behavior. Labeling strategy is a strategic decision, not just a technical one. Organizations own the consequences of their labels. The key takeaway is that labels define learning boundaries. Ground truth underpins trust in AI systems. Next, we examine how performance is measured using evaluation metrics.